Hi, this is Joe Maciars from A Tutoring Enterprises with another Apple Graph or Graphing Calculator video about graphing rational functions. Specifically, we're going to look at end behavior as x approaches infinity. Let's go over to the graphing calculator and get started. We've got a lot to do. All right, just a little quick review of some of the previous videos. In the last video, we had talked about an equation that looked a little bit like this. We've got a vertical asymptote at x equals 2. And our function basically goes in different directions around that asymptote. And that is a feature of the fact that there's an odd multiplicity. The multiplicity is the exponent that's right there in our equation. When that's an odd number, we're going to get this sort of feature where one branch seems to go to positive infinity and the other branch goes to negative infinity. Let's take a quick look at some of the other numbers that might do that. We got x cubed, we got x to the fifth, x minus 2 to the third, and then to the fifth, and then to the seventh, and so on down the line. So any of these odd numbers that we can put in there are all going to have this behavior of going in opposite directions, one going to positive infinity and one going to negative infinity. Let's go back to the first power again. And if we want this to sort of go in the opposite direction, that is, for example, on the left side of the x equal 2 of the vertical asymptote, we're actually going down to negative infinity as we approach the asymptote, whereas on the other side we're going up to positive infinity. I can switch that around simply by putting in a minus sign. And you see we get that. But the basic feature of the odd multiplicity going in opposite directions still holds. So it doesn't matter whether there's that plus or minus out front of the entire thing. All right, let's get rid of that. And we're going to go ahead and go back to this and now check out what happens when we make that an even multiplicity. For example, a 2, they're both going to be going off in the same direction. So that's x squared, x to the fourth, x to the sixth. They're all going to do the same sort of thing. Okay. All right, that's x squared. Now that was in the last video, and hopefully you've seen a link that might get you to that particular video. We're also going to have links to the various videos at the end. So if you're not real familiar with this behavior, you might want to go check those out, but you might want to wait till the end of the video. It's not necessary for some of the things we're going to discuss today. All right, well, let's go ahead and shut these two off. Another behavior we were looking at is what happens when we have the x minus 2, or the factor, in the top. And in this particular one, this is just a straight line equation. It has an x-intercept at x equals 2. In other words, whatever makes this 0 here is what we're going to get for an x-intercept. Whatever makes the bottom on this one 0 is what gives us a vertical asymptote, or a hole. We'll talk about holes in more detail in another video. All right, so again, we're interested in what happens with the odd multiplicity here. And so let me get up there and change that to a 3. And you're going to see what behavior is happening is that the graph is actually passing through the x-axis at that location. So that is what's going on there. If I make a fifth order, we see the same thing. Seventh order, same thing. Okay. Again, if I want to basically have it do different things on either side of this x-axis, all I have to do is add a minus sign. What I've got here on the left side of x equals 2 is the y values here are negative, whereas on the other side the y values are positive. So if I turn around and put a minus sign in front and hit return, now I've got the opposite behavior, but still the odd multiplicities are going to pass through the x-axis. So that minus sign, again, will have no effect on the passing throughness of the odd multiplicity. Now again, even multiplicity is going to do something a little different. And what's it going to do? Well, it's just going to touch at that particular point. So it's just touching at x equals 2. All right, now if I make it a 4, basically again the same sort of behavior. 6, it just becomes more box-like as we go along. 8, same sort of thing. All right, let's go ahead and change that back to a 2. All right, so that's a summary of the last two videos that we were talking about. Today we're going to study the combination of these two things. Now, in this particular case, you might think we might be looking at, well, we must be studying vertical asymptotes or x-intercepts or both or something. Actually, that's not what we're going to be looking at. We're going to be looking at what happens as we let x either go to positive infinity or to negative infinity. Now, what we're going to see happening here depends upon where the factors are, if there's duplicates top and bottom, and all kinds of good things. But as far as we're concerned, we're going to be looking for what's called the total degree on the top and the total degree on the bottom. Now what we're going to find out is the negative 2 in both of these is really not going to make that much difference as far as the extreme end behavior is concerned. Now I'm using the word extreme end behavior. I tend to use this with my students because there's also a type of end behavior which personally I would call middle behavior. That is a little different than extreme end behavior. So I want to talk about extreme end behavior. That is when we go really, really far away from the origin. Not just a little bit, but a lot. All right. The study is going to begin by basically examining the difference of the different multiplicities top and bottom. For example, I have an x minus 2 on the top and an x minus 2 on the bottom. I have both of those. In this case, I've got this one to the 6th power. I've got the top to the 4th power. What's going to happen? Well, as you might expect, I've got 4 of these on top. They're going to cancel with 4 of them on the bottom. I'm going to be left with 2 on the bottom. And I'm basically going to have something that's going to look like, well, in fact, let me go ahead and just turn it on. And you'll see what it looks like. And I forgot to make it green, so let's do that. Okay. Basically, it's going to look like y equals x, well, let's put a 1 over, x minus 2 squared, because 6 minus 4 will get us an extra 2 down here. And you'll see we get exactly that same curve. Now I'm going to change that to a different color just so that we can see it as something different. It is exactly the same curve, so I won't dash it. Okay. It should look like it's blue right now. If I turn it off, you'll see the green one that's underneath it. There it is. So these are exactly the same two equations. All right. Now, what I'm really interested in is what happens when x goes to either plus or minus infinity. That is, what is happening as x goes this way, and what happens as x is going this way. Well, you can see on the graph what's happening. Basically, this is approaching the x-axis. Now, why is that occurring? Well, it's occurring for the same reason that it would for y equals 1 over x, or actually in this case 1 over x squared. Now, this is a slightly different curve than the one we're looking at. It's actually pretty obvious. Let's close that and dash this line. And since this isn't the real curve, I'm going to dash it to emphasize that it's not. But what we're going to see is that when we zoom out of this, this discrepancy, this difference in the way these two curves look here will not show up when we zoom out, okay? And I'm going to show you simply by zooming out. So let's go take a look what happens. And what you see happening is all this detail stuff that's occurring in the middle towards the y-axis here, basically will get absorbed by the y-axis. And by this point, maybe here, definitely there, you can't even tell that there's anything different about those curves because they're both effectively been smashed into the y-axis. And furthermore, you can't see any difference here on the x-axis, the y equals 0 line, that is, of those two. They both look like they're the same curves as far as we're concerned. And so from this point on out, as we keep zooming out, these curves, for all intents and purposes, look the same. This is what we're talking about. This is our extreme end behavior. The extreme end behavior basically indicates what's happening when we go very, very far away from the detailed behavior, very zoomed out. And what that's basically telling us is we can ignore this as a lower order term. We don't need to worry about it. We only have to worry about the higher order term, the x with the higher power. Okay? We'll see some more of this, examples of this when I give you some details at the end, but I still want you to just sort of get a basic idea of this, so we're going to do a little bit more with this. All right, let's go ahead and zoom back in. See some of that detailed behavior. Oops, coming out. Okay. And let's go ahead now and change this. Let's make the bottom a little smaller this time. So it's still fifth order now. Fifth order is still bigger than fourth order, so what's going to happen is 5 minus 4 is going to end up being a 1. Okay? So what we're going to see here, let me turn this one off for a moment. This one is our green curve. This is the actual curve that we've got plotted. And this one is the curve that's basically these two put together. It's simplified. But it's exactly the same. It's right on top of it. Okay? So let me turn that off. And let me turn this one back on. And basically the behavior of this, if I'm ignoring the -2, the extreme end behavior of this kind of curve is not 1 over x squared, but rather 1 over x to the first, or just 1 over x. And again, it looks very different. The red line inside, in this close-in neighborhood, looks very different from the green line. But when we zoom out, we're going to see again the same behavior. So let's zoom out and check it out. Again, as we zoom out, the y-axis is going to kind of absorb all that detail behavior. And at that point, we certainly can't tell the difference between those two curves, whether it be involving the asymptotes or the horizontal asymptotes, the vertical or the horizontal. Basically, this looks like a big X as far as we're concerned. Okay? And again, that's what we're talking about with our extreme end behavior. All right, now let's go ahead again, zoom back in. Oops, wrong way. Okay, one more. All right, and let's go ahead and change this fifth power to a fourth power. Well, now these two things are the same, and they should exactly cancel, and that'll end up being the exact same thing as x minus 2 to the 0th power. Now I'm just going to erase that and put in x minus 2 to the 0th power. And either way, we get what looks like y equals 1. Now, there are some issues with holes, and I'm not going to discuss that at this point. My main idea is to get at the extreme end behavior. Now, what we're going to see here then is that this is slightly different behavior than the previous two that we saw. Previously, we had the line y equals 0 as our horizontal asymptote. This time we're seeing the line y equals 1. All right? And so that line is our horizontal asymptote, whether we look at the simplified version of it or the more complicated version of it. So in essence, there's no real value. If I put in x to the 0 here instead of x minus 2 to the 0, that also will appear right up on top. So there's no real difference between these curves. Okay? And so I'm not even going to bother to zoom out. They're just going to look the same. But I want you to note that when these two powers are the same, we now have a constant that's other than 0 for our horizontal asymptote. So that's a slightly different behavior than the previous two. All right, let's again shut those both off, go back over to here, and we will continue to decrease that power on the bottom and see what happens. Well, now there are 3 x minus 2's on the bottom and 4 on the top, so 3 of them are going to cancel, top and bottom. We're going to have an x minus 2 left on the top. Well, what do we get? Well, we're going to get x minus 2 to the first power. And that's going to look like this. Actually, I should have put this one in first. Let's turn that one off. And there's our green line at that point. And here's the blue line right on top of it. Again, just showing that that's the simplified version of this. And we're going to go ahead and put in, basically, x to the first. Get it up there. To the first. And we get a line that looks like this. Now, this time, these two curves are not lying on top of each other. They look very different. Now, the type of asymptote that this is neither vertical nor horizontal. This is definitely termed in the textbooks as oblique. Now, what I've never really figured out for sure, and my impression is that an oblique is a line. It's actually a line that's a dashed line that the curve will approach. We're going to see that there's other kinds of asymptotic behaviors that are not lines. So whether they would call those oblique, I don't think they would, but if they do, then so be it. But for me, this is an oblique asymptote. And in terms of the extreme end behavior, let's go zoom out again. we're going to find that it makes no difference whether I'm looking at the blue curve or the green curve. Let me turn the blue off. The blue or the green curve, it's not going to make any difference. And I think I zoomed in. I need to zoom out. Let me keep zooming out, because as I zoom out, the green one begins to approach the red one. And no matter how far I zoom out, in effect, the red one never moves. And the green one seems to effectively be the same as the red one. In other words, the difference between those two curves when I'm out at this scale is so small that we can't even perceive it. So the extreme end behavior of this is that y does equal, roughly, just x. And that's what we're looking at. From here out to infinity, no matter how many times I click, these two curves are going to be indistinguishable as far as I'm concerned. Okay. All right, let's zoom back in. And we're going to take a look at increasing the bottom power. Or I'm sorry, decreasing the bottom power one more time. So there we have it. Okay. So now we have this. We have x minus 2 to the fourth on top and x minus 2 to the second on the bottom. 2 on the bottom, 4 on the top. 2 of them will cancel, leaving x minus 2 squared. Now, you should know that that is a parabola. So there it is. It's x minus 2. It has an even multiplicity at x equals 2. So it's just going to come down and just touch at x equals 2. So let's go over to the blue curve and just emphasize that, yes, that is indeed what it is. If I put x minus 2 squared, that's the resulting simplification right on top of the green curve as we expected. We'll go ahead and turn that off now. But the extreme end behavior is not x minus 2 squared, but rather x squared. And from this point of view, looks very, very different. Okay, now let's zoom out and show that these two things are the same. And you might be a little surprised. You might suspect that, well, there's no way that these two things are going to look the same. Well, there is a little bit of a problem, because as we go in, you can see that it appears to be getting narrower and narrower. And that's because of the fact that basically as the x goes up, or as we scale out on the x, we should be scaling out by effectively y squared, because y is equal to x squared. So for every amount that we go out in the x, we're going out the same amount in the y, and we should go out the square amount of it. So since we're not doing that, what's happening is they're approaching the y-axis. You might object to that and say, well, wait a second, just because they squeeze into the y-axis, that's not a very good argument for they're the same. And I agree with you. So what I'm going to do is I'm going to go to the frame limits and I'm going to adjust this. Unfortunately, I don't have an automatic way to do this, but let's go ahead and just call that 3,000 and call this or negative 3,000 and this 3,000, and let's see what happens. Now, in effect, what I've done is I've just squashed the y-axis. And you can see it looks a little bit more like it did when we first started. Now, you can still tell that the green curve is a little bit offset from the red curve, but it's, if you didn't know better, you could look at it and say, well, I might miss that. All right, well, let's keep zooming out and see what happens. So we're going to zoom out 3 more times, and we're still getting the same behavior. Fixing that once didn't solve the problem when we zoom out. So now let me go ahead and change that to a 7, and that to a 7. By the way, this is scientific notation, so I'm basically multiplying by 1,000 when I change a 4 to a 7 there. And again, we widen it out. Now at this point, in fact, I widened it out quite a bit, but can you tell any difference between the green and the red? I can't. Let's zoom out a little more. It'll start to look more like the curve we were looking at. I don't know about you, but I sure wouldn't want to bet which one was more to the right than the other on this one. And that's the kind of thing we're talking about. So this curve, or this one, it makes no difference. I guess let's turn on the blue one. That blue curve compared to that curve, the y equals x squared, are fairly indistinguishable when we've zoomed out far enough, and that's the point. The point is we only have to worry about the x squared in the very far out behavior, the extreme end behavior. That's what we're talking about. Okay. Let's do one more, and then we're going to do a couple of quick examples and try to get out of here because I know this is going to be a long video. Let me close these two. And let's go ahead and reduce the power down on the bottom again by 1. We now this time have 1 x minus 2 on the bottom and 4x minus 2 is on top. One of them are going to cancel. We're going to get x minus 2 cubed. And I'm going to equalize the axes, and I'm going to zoom way back in so we can see what this looks like in detail. There we go. We're getting there. Okay, so I think that's pretty good. There's the x minus 2 cubed is what this will end up being. It's an odd multiplicity, so it's basically passing through x equals 2. Let's verify that by changing this to x minus 2 cubed and verify that it's right on top of the green curve, and there it is, exactly on top of it. Let's go ahead and turn it off now. But as you might suspect, we can ignore this minus 2 and write this as x to the third. This is our extreme end behavior. And again, inside here, these look very, very different. So again, we're going to zoom out to see that, in fact, in terms of the extreme end behavior, they're the same. Now again, we have that same issue with the fact that it's just crunching itself into the y-axis. So we're again going to go over to the frame limits and kind of pump this up a bit. So let's go minus 10,000, actually no commas, and go 10,000. And wow, that didn't do too much. Let's do a little bit more then. Okay. Let's add another 0. Well, maybe 2 more zeros. Okay. There we go. Okay, so now it's looking a little more x cubish. And it is very difficult, even at this point, to start telling the difference between those two. But you might be able to just notice the red's just slightly, ever so much to the left of the green curve. So again, let's zoom out a little bit more. So zoom out, zoom out. Now, clearly at this point, I can't really tell the difference. Can you? Let's go hit the view. I'll jump this up to, I don't know, let's make this 10. See if that'll be enough. Oh, maybe 12. Do that. Whoa, that was way too much. Okay, well, let's zoom out a little more. There we go. You just zoomed in. Okay, well, there you go. I can't tell any difference at all between the green and the red. So there is, now we're way, way out there, but here's the point. If I now start to continue to click zoom out, how many more times can I click this to get to infinity? Well, remember, infinity is not a specific number, so that means for like the rest of my life. So from now to the rest of my life of clicking on the zoom out, these two curves will basically look the same. Now I'll have to keep playing with the frame limits to actually see it, but that's the point. That's what we're talking about with extreme end behavior. Okay, now let me give you a little more concrete examples and problems that we can look at in real life. These were very contrived examples, meaning that I set them up to be really nice. So let me pick out some really ugly ones. I'm going to start with the bottom here. Let's go with x to the 6th plus 5x to the 5th. And then let's do a minus, I'll stay with x to the 4th, plus 3x cubed. I guess I'm not being all that original about this. Minus 2x squared. Let's go plus x and minus 1. Okay. And now the top, we're going to do something similar. Let's do, I don't know, 10x to the 4th minus 7x cubed. I'm just picking these numbers random. This is just out of my head, top of my head. 3x squared. Let's have minus... Now, I can pick really, really ugly numbers, but there's no need. That's not the point. I just want to get different numbers, that's all. And let's go plus 5. All right. So, what are we going to expect to see? Well, first of all, let me equalize the axes. I think that's going to try to graph that. No. Okay. And let me zoom back in. It's going to take a little bit to get in there. But not too much. There's 8. Okay, we'll do one more. That's good. Okay. What do we expect to see when we're going to do this? Well, in terms of extreme end behavior, well, detailed behavior, we have no idea what it's going to do in the middle of this thing. It could be, it's a mess. But what are we going to see? Well, our highest order on the top is this 10x to the 4th. And the highest order on the bottom, well, is going to be this x to the 6th. And so the 6 is bigger than the 4. basically, if we ignore all the rest of this stuff, the x to the fourth will cancel the x to the sixth, and we're going to expect something that looks like, well, it's still got a 10, so it's going to look like 10x squared. Now, I'm going to have to zoom out for us to see all that other behavior, but let me put in a 10x squared for this. And we're going to turn this off. Now you can see, right here, this green or this red curve doesn't look anything at all like this curve. And let's go ahead and let's change this to something else like I don't know, a purplish color. Let's do the strawberry. We're going to do strawberry. Okay. All right. Well, let's turn this off for the moment, and let's zoom out a little bit and see what this looks like. And wow, that's pretty, we got some really weird stuff going on over here, some really curvy stuff, some very sudden, almost hard turn there. This is what's going on with this entire curve. Now, if we click on this, this looks very different in the middle. But look at what's happening on the outside. Okay, the extreme end behavior, remember? If we zoom out, and I should really kind of do that, these curves look the same. They're right up on top of each other. They're y equals 0. That's our asymptotic behavior associated with the power on the bottom being bigger than the power on the top. The highest order power on the bottom being bigger than the highest order power on the top. All right. Notice, now I guess I shouldn't have put a 10 there because the 10 makes it look like maybe I'm talking about the 10 is the biggest thing. That's not what I'm talking about. I'm talking about the x to the fourth is the biggest thing. We're going to see that. In fact, let me emphasize it. Let me get rid of that. Let me call it a 2. We'll just do that. In which case I probably ought to go back over here and call that a 2. So I'll do that. And really, it doesn't affect anything for the extreme behavior at all. And you see, it's the same thing. Y equals 0 is our horizontal asymptote. So we get that horizontal asymptote, y equals 0, when the bottom exponent is bigger than the highest order top exponent. Okay. Now, let's go ahead over to this, and we're going to wipe out the x to the sixth. What are we going to see? Well, the bottom is still higher. We still got an x to the fifth compared to an x to the fourth. Now, theoretically, we have a 2/5 here, and that 2/5 goes along with what we're talking about here. So this should be now not x squared, but a 5x, and we'll have 2 over 5x, which will be the asymptote that we have here. Now let's zoom in again, just kind of see what's going on. Very different curves there. Okay, very different. Okay, but again, in terms of zooming out, both have the same horizontal y equals 0 asymptote that we were expecting. So there it is, right there, right there. Okay, well, let's go one step further. Let's turn these off. And let's go take a look at, again, killing another term here from the bottom. Let's keep that minus sign. All right, but we'll get rid of that 5x to the fourth. Whoops, I didn't want to do that. Last one. There we go. And let's go see what that looks like. Well, these are pretty interesting. It's all this dipping and weaving and all this thing is doing. Notice we've got the little thing coming up. All right, and what's that going to be? Well, we've got 2x to the fourth over negative x to the fourth. The rest of that we ignore, so that's going to give us basically a negative 2. All right, in other words, we're expecting an asymptote at y equals negative 2. And there's that line. Now, check it out. It's not y equals 0. It is y equals 2. This is where this curve is approaching on both sides. So all the detail behavior is a whole different question, but in terms of the extreme end behavior, that's all we got to do is look at the leading or ordered terms. All right, let's go ahead and take a look now at what happens when I take another term off. Well, that means we're going to get rid of that negative x to the fourth. We're going to have 3x cubed. What are we going to have? We're going to have 2x to the fourth over 3x cubed. Well, that's going to be linear, right? That's going to be x to the fourth, x to the third. 3 x's will cancel. We'll have an x. We'll have 2x over 3. Well, let's go ahead and put that in. It becomes positive again, 2x. Actually, let's put the 2/3 in. We'll go back and put the x on the top. So 2x over 3. So this now becomes our asymptote. Okay? Again, looks very different. And this is what I was calling middle behavior. This middle behavior starts showing up as soon as you get linear equations or linear asymptotes and higher. In reality, there's an actual asymptote here that this is, and it doesn't look like it would be. It looks like this might be a little lower. Actually, I think it is. And this is a little higher than a line that you could put between them. And that is the actual asymptote. But for extreme end behavior, not for middle behavior, but extreme end behavior, the red line is our asymptote. Now, let's zoom out and show that. So here we go. Whoops, wrong direction again. I don't know the difference between in and out. It's obviously a problem. All right. And I should click off so you can see it. And there we go. I think around there, very difficult to tell that there's two lines there at all. It all just looks like the pink line. But if we click off on the pink one, there's the dashed red one underneath it. Okay. All right, let's continue the process, and you really should be getting a pretty good idea now. Let's zoom back in. Maybe one more. There we go. All right, so what are we going to get rid of now? Well, of course, the 3x cubed. Let's get rid of all that. Okay. This time we're going to have the 2's canceling. We're still going to have that negative sign in totality. And then we're going to have an x to the 4th over x squared. Well, the x squareds are going to cancel. We're going to have an x squared left on top. We're going to have negative x squared, which should look like a parabola opening downward. Okay. Well, let's find out. Let's hit return here and see what happens. Well, this doesn't quite look like what we have in mind. It is opening downward. It is kind of parabola-ish. But is it what we're looking for? Well, let's find out. Let's go change this into the negative x squared that we said we should be getting. Negative x squared. Well, it sure doesn't look like it is, but again, we can do this thing where we zoom out and we'll have to fix the scale of this. Let's zoom out a couple more times. And then we'll hit our frame limits, and we'll change this into, I don't know, 110 to the 5th. Maybe that'll do it. 110 to the 5th. Okay. There we go. I guess I could go a little bit more. Let's jump it up a couple more. Really widen it out. Okay. And, you know, can you really tell that there's a dashed line there? I mean, I can't. I'm not seeing it. If I turn that off, there is the dashed line. So it is there. But from this point of view on out, we can't tell the difference between these two curves. Okay? And so we can keep on doing this. We can keep playing game. We can get rid of this term. We're going to have an x to the 4th over x. So it'll end up being 2x cubed. That's when we get rid of this. And so on down the line. So what you can see me doing is I'm basically ignoring everything else on both the top and the bottom except the two leading terms and then just simplifying that. And that tells you what your extreme end behavior is. So it's not that difficult when you have these complicated things like this. It's when we're in more factored forms like this that we actually have to worry a little bit more about the zeros on the top and the zeros on the bottom and all of that good stuff. Okay, well that's more than enough for today, I'm sure. I don't know how long this video is, but it's pretty long already. So let's get out of here. The next video, what we're going to do is start putting this information together, and we're going to start to learn how to predict what a rational function is going to look like. Now I'm trying to think if I even want to talk about wholes within that video, or I might have to do a separate video for that. I'm very tempted to try the other. I don't know. I'll have to think about it. But sooner, within the next video or the video after that, we're going to start to look at, you know, here's a given rational function. What does the sketch of this look like? What does the graph of this look like? And we're going to be able to do that, figure it out, just by pulling it apart into these factors and figuring out what the zeros on the top are, what the zeros on the bottom are, what's the y-intercept, which we'll talk about then, and what's the extreme end behavior. And in some cases, we're going to have to talk about middle behavior. So we'll do that in some of the next videos, and I'm going to do many videos. I don't know, maybe 5 or 6 different examples, because there's so many different flavors of these rational functions that you really need to see more than just one or two. So we're going to do that. All right. Well, that's it for today's video. Let's go back over to the closing screens. Again, my name is Joe Macias from A Tutoring Enterprises, and this was Graphing Rational Functions and Behavior as X Approaches Infinity. A little plug for my business. I'm an online and in-person tutor, and I tutor in physics, math, chemistry, and engineering, and there's all my good information, my website, my email, my phone number. So give me a call if you're interested in getting some help, and we'll get you some help. Please remember to hit the like button, comment, and tell me what you're thinking about these videos. Let me know if you want to see something else. I'll try to cover something that maybe you have a question about that maybe I didn't already cover. And subscribe, and that way you'll get updates to all my videos. If this video really helped you out, feel free to donate $1 to my PayPal account. I'm trying to get better equipment and basically get better information for you guys. So, and I'd really appreciate it. So, there you go. Let's go over to a white screen. And this white screen, I promised you some links to a couple of the past videos that we were doing. Also, some of the future videos that I told you about. We'll have that here. I'm also hoping to have a video index of some sort, of directory that can lead you to all the different types of equations that I've been doing and working on, all the different math, and hopefully some physics and tutoring videos too that you might be interested in. I haven't done any of those yet, but look for them in the future. I'll update these links as we go. So I appreciate you watching the video, and have a great day. Check out the next one.